Systems Private Limited, working for some financial clients in US. So that's my simple introduction. So with this, we will move on to the session. Um, the topic for the discussion is we need to go through some of the concepts behind compilation and parallelizing and vectorization. So before entering into the concept of parallelization and vectorization, I feel it is good to
I will tell you
have
what's weird.
some discussion among the concepts which you have learned so far. For me, I am going to touch on some of the things like um, GNU-based GCC compilers collections. Yes, sir. I am about to share my screen. Before that, I'm just giving some introduction. So I'm going to have some direct programming session. So I'll share a while. Is that fine to everyone? I request the participants to kindly respond in the chat. I am looking at the chat parallelly. It is good for me if I get the feedback as soon as possible. Thank you. Thank you for the feedback. Yeah. So let us proceed with some basic things. Let me share my screen. Can you see my screen?
Yes, sir. It's audible. It's visible, sir. It's visible, sir.
Thank you. 1 minute. Hope you are seeing some editor. I am showing my Visual Studio Code editor. I think this is visible to everyone. Great. Now, before moving on to the concept, I would like to refresh some of the things as I already told. First, let us look into the concept called the tool chain. So I'm just opening a new editor, tool chain. So there, especially we are going to discuss about GCC tool chain. Okay, so here, when since the course is related to the compiler design, it is the best choice for choosing the language for the discussion. Entire discussion is I prefer it is a C programming language where we can deep dive into a lot of things and we can play around with some of the all the fields, all the operations performed from the source code to the executables. So there is a source code. For example, if we take a C programming language, file name .c extension, that is a source code. And finally, it will be end up with the executable code, which will be directly executed on the particular platform in which it is compiled for. So keep this in mind. So we will proceed with the tool chain. Tool chain is actually a chain of sequential steps or sequential processes to be done in order to make the source code into an executable. That is called a tool chain. Especially it is the concept derived from Linux based environment. So can you tell me what are the steps involved or tools involved from the compilation or from the source code to make the source code into an executable? What are the stages of compilation or stages of making a source program into an executable? Can you tell me the stages? First, let us assume that it is a source code. So the next it would be any idea? Let us move on directly to compilation. Okay, compilation. So once the compilation is done, my question is the compiled code directly executable by the processor or not? Say, for example, if you compiled a C program, whether that particular compiled program is eligible or is ready to be executed in the particular processor or not. You can answer in chat wherever it is possible. Hello. I'm expecting some answer in the chat. Okay. Then I'm just proceeding. I hope I am audible. Did you all get my question? Okay. Okay, anyway, I am proceeding. If you have any clarification, please let us know. Source code, then it is compiled. Then we need to have a linking process. The last stage is loading. Okay. So the source code should be compiled, then it should be linked and it should be finally loaded. So these are all the steps involved in most of the, irrespective of the platforms, programming language or any platform. This is what the set of stages to be followed. When you give the source code, it will be compiled. Maybe some kind of language will be for the interpretation. Then instead of compilation, there it will be an interpretation. After that, we need to have, obviously, we need to have a linking and loading in order to make the program executable. Got it? Yeah, Naman, if I spell your name correctly, Naman, thank you for that. Yeah, exactly. We cannot directly execute that compiled code. The compiled code basically does not linked with certain set of functions. So for example, a program or a project can have multiple files in it. Each and every file can have its own functionality in it, because we used to program in a modular fashion, right? There is a modularity in every implementation of the application. So whenever there is a file, the file can have multiple classes, or a class can have multiple functions in it. So the function, each and every function is unique to its purpose. So if you define any function, at least one function, whether it is a user-defined function or if you are going to call any predefined functionality, then obviously the compilation step alone is not only needed for making the program executable. So thereby, we need to have a certain set of reference or resolution of addresses for a particular functions or set of functions called or invoked. That should be made. That should be assigned with the source, compiled code. So the resolution of addresses within the compiled code's output is called the linking. Once the linking is done, then it is the job of the other tool called loader. It is a compiler. Compiler is doing compiling, linker is doing the linking operation, resolution of addresses with the user-defined and predefined functionalities within the application. And the last one is a loading. Loading means finally we will be getting the executable as a machine level language code corresponding to the particular processor. Once it is ready after linking, then it should be loaded into the memory, the primary memory of the particular system where you are going to execute. I mean, it is a RAM. So the executable code should be placed in RAM. Then only it is eligible for uh, real execution by the operating system. So then the operating system will take over control from the specified location of the starting address of the program. Then it will take care of execution one by one as per the sequences of program in the machine level language. This is what the steps involved as a overview. As an overview, these are all the steps involved in the GCC tool chain. Is that clear now? Got it. Thank you. So now we'll proceed. So now I want to uh, go little bit in depth on the compilation. So there is a system. So these three things are called system softwares. All these three things are system softwares: compiler, linker, and loader. Okay, system softwares especially. They are not simply an application softwares. Can you tell me why it is called system softwares? What makes the difference between the system software and the application software? Keep that in mind. Maybe we will discuss that later. So my question is, I request Naman to make a note of it. I asked a question called mm, why we call this compiler, linker, and loader as a system software other than an application software. Kindly note it down, Naman. We will discuss later. Now, as of now let us go in depth on compilation. The compilation is again doing a lot of operations in it. The real processing of conversion from source code to the executable is happening in the compilation stage only. Okay, linker and loader's job is a mild kind of thing, but it is major one, but it is a mild one when comparing with the compilation, because the compilation will compile, will accept each and every line as a set of block as an application, and convert the entire blocks or units in an application into a machine understandable form. But obviously it is not directly executable because there is a linking needs to be done there. the compiler is actually the translator. Linker and loader are not at all a translator. Compiler is the only translator. Interpreter is also a translator in other set of languages. Now, if you take a compiling stage, the compiler is having one of the first step called pre-processing. So it is done by pre-processing. And the real translator, the real translation, the compilation. Once the translation is done, there is another last level operation carried out by the compilation unit is called optimization. So these three steps are very important steps when we consider or learn compilation. Pre-processing, the real translation, and the optimization. That is what happening in the entire compilation stage. Now let us go one by one. What is meant by a pre-processing? What will be handled in the pre-processing stage? Let us keep this and move on to a set of program. I just created a set of example, very simple examples so for our walkthrough on this compilation as well as linking and loading. Can you able to see this? Is it visible to everyone? Do you want me to increase the font size or is it enough? Great. So now it is a very simple program which is having hash include stdio.h. Main function is defined with two lines. Just printing hello world with a new line character and returning 0. So since I mentioned that the main function is going to return some integer, the default value, the successful execution of the integer the main function is obviously a return 0 value. Other than 0, it mentions there has been some issue happened in while executing the program. It is not a proper successful execution. That's it. The successful execution will return 0 to the caller. The caller is operating system. Very simple. Who is going to call this function? Who is going to call this invocation of this function, main function? If we have any subfunction, I don't have any subfunction here. Assume that there is a function called printf. Printf is invoked by main function, but main function is invoked by the operating system. Got it? Via the loader. So since the return data type of this int function, the main function is int, so I just added this line and it is a very simple function. So what would be this line, the first line? What is Perl? Any idea? We have a line hash include stdio.h. Yeah, Anuru. The question is, okay. The question is why we need this line hash include stdio.h. Yeah, I got an answer. Response header file for input and output. Great. Standard stdio means standard input output dot header file. H means header file. We will create our own header file, user defined simple header file for our explanation purpose one by one. Meanwhile, let us discuss something on here. So what is the content? What may be the content in header file? I got some response. It gets pre-processed before compilation. Great. The compilation step, as we discussed, a compiler is having three set of operations. The first one among that is pre-processing, then the translation, then the optimization. That is going to happen. So here, um, can you make it a little bit clear? So what maybe the content of header file? Uh, as per our assumption, we have used a predefined function called printf. So the printf function is comes under the output category. So it is a standard output function. This function is related to standard output. What would be there in this .h file related to this function? That is what my question. Have you got my question? Okay, anyway, I'm proceeding. If you have answer, please provide it in chat. I'm looking at it. Great. So this is the, so this function is predefined function, correct? Predefined function, or you can call it as pre-compiled function. What is that? What is meant by a pre-compiled or predefined function? It is a set of code which is written in kind of assembly based language, or maybe in C or something else. Once the particular code is compiled into the machine level code, then the compiled version of that one, or the collection of compiled version of the code, will be present in the library. You got it? There are two types of library available: static library and the shared one. Static library and the shared library, that we will discuss later. But again, for the discussion purpose, I am just highlighting those things. Static library and the shared library. These libraries are called static libraries. Whenever, if there is a set of functionalities compiled, if we have certain functionalities to be used very frequently in our program, then those can be compiled, and the set of compiled unit can be made it as a static library. So this printf function definition is part of the static library, but this header file does not have any code in it. You got my point or not? If you take a function, there are three things we need to reveal on that. There is a for a function, what are the things? The one is there must be a definition. There must be a definition. Two, So one is the definition. Another one is declaration. The third one is access or call. Very important. You got my point. Guys, are you here? I hope this is not boring one. Thank you. So definition, declaration, and access are called. Okay. So let us take this program, simple program. We are using printf. Okay. Which one it is? Is it a call, definition, or declaration, or a function? Where it is? Predefined in the library. Great. Predefined in the library means the library has the pre-compiled version of a particular function, printf. I mean the definition. So the library should have the definition. Library should have the definition. Call is in the program where we are going to use. So where is the declaration? Where the declaration will be there. Why we need declaration of a function? Or what is the structure of the declaration? So this, as per this program, printf is call. You know the definition, since this is the pre-compiled version of the function, that should be part of the library. Which kind of library? Already I told you there are two types of libraries, static library, and another one is the dynamic one called shared objects or shared libraries. So these definitions are comes under the static library. The other one is the declaration. So where the declaration is there, the declaration of every functionality, the predefined functionality or pre-compiled functionality should be there in the header file of the corresponding compiler. See, GCC compiler is maintaining stdio.h as the header file, which is meant for maintaining all the declaration of the predefined functions which are related to input output operation only. Does that make sense? You can simply Google and you can check what is the content in stdio.h. There you can find one of the line with the printf and one of the line will be defined, will have the declaration for the scanf, all the file related functionalities, something like that. Everything will be part of this file. This file is going to have the declaration is in the header files. We do have several header files for different categories. Something related to if you are going to use any mathematical functions, then there is a header file called math.h. Like that, we do have different set of functionalities, I mean header files in it. That differs on different languages or compiler. but this is what the basic process. Is this clear now? Hopefully. Now I am going to just compile the set of process one by one. Then we will move on one step ahead with the way of compiling the program in GCC. What are the different ways in which we can visualize the tool chain, the loading, linking, something like that in a step, in a step-by-step manner. Now I am just saving this file and moving on to my window. I'm using WSL Linux Ubuntu. So here I have a set of files here. So we have a file called hello.c, right? Let me compile that first. So gcc GNU compiler collection, GCC is the command. Simple hello.c. Just I'm pressing enter. What will happen? Nothing has happened. If I give ls, I will be getting the same set of files over there. So among that, we have a file called a.out. That is the recent executable file generated by GCC command. So I would like to remove that file just for your clarity. I removed that. Now we don't find any a.out file here. Now let us again, I'm compiling this code gcc hello.c. What is happening? Now there is a creation of a.out. So simply /a.out will give you the response for the program. So that is what we mentioned in the printf to be displayed. This is what here. So this is the step gcc space filename.c. It is a very normal way to compile and link, and finally to run the code. Okay, so there are 3 stages in it, right? We have discussed compilation, linking, loading. Among this, the first 2 stages are done by this command directly, gcc space filename.c, and it finally creates a file called a.out. By using this a.out, this is an executable. We are running /a.out. This command actually invokes the loader. Okay, this command invokes the loader to load this executable in the RAM, and by means of operating system, it will be executed, and finally you will be getting the response. This is what happened. So this step is combination of both compilation and linking, and this step is loading and execution. And we do have different ways in which let us split one by one. Can we have the compilation alone first? Is there any possibility? Let us do one by one. So for example, gcc space hello.c followed by hyphen o for executable, followed by hello. Do we have any hello? Yeah, here we have hello. So before that, what I would like to do, I can remove now. We don't have any hello a.out and test. Okay, now our focus is hello.c. I am going to compile this in different way. GCC space hello.c followed by -o, o for creating an executable. Again, an executable will be created. It involves both compilation and linking, but in a different way. By adding the parameter -o, we need to mention what is the name of the executable you are going to generate. Hello.
எடுக்காதீங்க நம்பர்.
Now, if you search, you can look at something called hello. It is created, but there is no a.out. Now, we are redirecting the a.out, default a.out to hello by using the flag called -o. -o flag is used for, can you tell me? What is the purpose of -o flag? It is used to perform both compilation and linking. Finally, it will give you the user-defined name for the object or the executable. If we ignore this, you will get a.out. Otherwise, you can name it as hello. This is the best practice to be followed whenever you go with multiple functionalities or multiple files in a program. I'll show you. There is a tool called make. By using that, we can compile sequence of set of files. Thousands and thousands of files in a program in an application can be compiled one after another based on the dependency by using the make file. That I will give you a simple example in the later session. Now we have hello. So I'm just giving /hello. So it is giving you the same response. Is it clear to everyone? Fine. Now, one minute. It is a very simple example. So before going to the different stages of compilation processes like separate compilation, separate assembly, separate predefined, converting a source code to a set of, or exploring the source codes, pre-processing directives, separate compilation, separate linking, like that. I would like to show you some more example with multiple files in it and how to walk through how to play around with the multiple files. And initially we have only one file, which is hello.c. Now we can have some set of files in an application, how to play around with it. Okay, so for that I'm going here. Let me create a file name, hello underscore fn.c. Okay, hello function.c. One file. There I'm just going to include stdio.h, and I'm going to include the user-defined header file hello.h, which I mentioned earlier, right? We can also create our own user-defined header files, which is ultimately going to have a set of function declarations. That's it. Still, uh, I am not getting any response from you that what is meant by declaration. If you have any idea, please post it in the chat. I'll look into it. So here, what I'm going to do, so I'm going to define a function called hello. And this function is going to accept an argument, some const character star name. It's a constant character pointer, and it's trying to print up just using %JS for the string display. Name. So whatever it is passed, it is just accepting and displaying. That's it. So this is what in hello fn.c. Just we defined a new function hello. That's it. Then we are going to define a header file. I'm going to create a new file hello.h. It should have the syntax of this function, the signature of this function. The signature of function is this one. I just want to copy this. Where it is dot hello. Okay, here. I just want to paste it. And I need to add semicolon. That's it. This is what the declaration of a function. Declaration of function means it is the signature of the function, the name of the function, followed by what are all the arguments and what are all the types of an argument and what is the return data type. That's it. Name of the function, number of arguments along with its signature. Signature means the data type, and finally the return data type of the particular function. This function is going to accept only one argument of data type const character star pointer, character pointer, and it is going to return nothing, so it is void. That is what defined in hello.h. And we are including that hello.h over here for making this function's declaration possible over here, inline over here. And finally, the missing thing is main function. So let us define a main function main.c. I'm going to make a file main.c. So within the main.c, what I have to do, I have to include, because I'm going to use the function hello, which is part of the hello underscore fn function, which is part of this file. This function is defined here. I'm going to use this function or access this function in main.c, where it is main.c. So that I have to include the declaration here. So the declaration, since this is the user defined function, a header file, I am enclosing that by hello dot within the quotes, not the angle brackets. It is deep. Whenever any set of file is enclosed within quotes, a compiler used to search the particular header file within the same scope or within the same directory location, current directory location. We are for the simplicity, we are maintaining the hello.h file in the same directory location. And I'm going to define main function int main, no arguments. So within the main function, what I'm going to do, I'm going to invoke hello function with some string. I'm just passing world. This is the character string. Just return 0. So this is what the very simple example to demonstrate multiple files usage for an application in a C application. So this C application is having 3 files, one header file, 2 .c files. One of the .c file is the main function, main.c, where main function is defined. From there, the entire execution is going to start. From the main, I'm going to invoke this, where this is placed. This definition is part of the hello underscore fn.c. And for the sake of signature manipulation, the signature of the hello dot user defined function is maintained in hello.h. And fortunately, this is included in the main.c file. Is this one clear to everyone? Now we need to compile this set of functionalities as a bundle. I am moving here. What I have to do? So I have two .c files, main.c, hello underscore fn.c. I need to compile these two C files as a whole in a single command. So it is again a simple command, gcc space main.c followed by hello underscore fn.c. Got it? If I directly run this, what will happen? It will generate a .c file, a.out file. If I run a.out, you will be getting hello world. That is what I'm going back. World is passed from hello. What is in hello underscore fn? Hello. So this word hello is appended with the name of the argument of the hello function. Does that make sense? It is just appending. So it is invoking and it is working fine. Now instead of using a.out, as we discussed earlier, so there is another way, gcc main.c hello underscore fn.c followed by -o. Okay, I want to generate a common user defined name, new hello. Okay, new hello. So it is going to create a new hello file, executable file. Here, look here. Now I can directly run this new hello. This is what the new executables. Does that make sense? Now, what I want to do is little bit go deeper into that. Is there any possibility to compile each and every file like main.c and hello underscore fn.c separately? There is a possibility of separate compilation. Clear, make it a note of it. If you pass all the C files, source files, as a collection of arguments to the GCC file, there will be a compilation and a linking will be done, and you will get a common file. If you're interested to compile main.c alone, hello underscore fn.c alone, then the output of the compiled code needs to be merged to generate a new executable. There is a possibility. That is also possible. But that is the real area that is used in the reality. Now let us proceed further. Now, what I am going to do is going to separately compile main function. How to separately compile? That is what my question. If I use -o, it is the combination of compilation as well as linking. But I don't want linking. I want only compilation. How it can be done? That can be done by using the new flag called -c. -c for compile only. So -c main.c. That's it. If I do this, we will be generated with a new file called main.o. Maybe for the sake of simplicity, I just want to remove for your better clarification. I am going to remove all start.o. So now this entire directory does not have any object files, .o files. So now again, gcc space -c main.c. So there is a creation of main.o file. Okay, it is an object only file, not a linked one. Similarly, what I have to do, I have to create a hello underscore fn.o file, main gcc fnc hello underscore fn.c. If you look at that, there is a creation of now what is the next step? We have a compiled version of the both source codes, both .c files. We obviously need to link. How it can be linked? So we have a flag again. We have discussed the already discussed about the flag called -o that can be used here for only doing the linking because we have already done the compilation. So now let us do it. GCC space main.o followed by hello underscore fn.o followed by -o for only linking. New hello link only. Okay. So what I am done. So once it is done, it is creating a new file, this one. So with that, I'm going to execute the new hello link only. So it is executing fine. Does that make sense? Is it clear to everyone? So what we have done, we have compiled both of the source files separately by using -c, which in turn returns .o files respectively. And we used those .o files of the compilation as an input to -o parameter flag. The -o is for linking. Actually, it is O is used for both compilation and linking, but as an argument, we have only passed main.o hello underscore fn.o as an object file to this O flag for this compiler so that it accepts these two files as an object file, already compiled file, and it links those two files to create a new executable. So far, is it clear? I hope it is clear to everyone. We will move on further. So what I would like to do is, now I am going to do some changes on this call. Sorry, this is not a call, this definition. Where is a call? It is in main.c. Okay. Now I am going to make this as everyone with some explanation. So just updated this main.c. So now I want to reflect the changes in this object. What I have to do? I made a change on main.c. I have not done any change on the hello underscore fn.c. Just look at the scenario. We are working on the very simple example of multiple source code C program application. There we have two source code files, main.c, hello underscore fn.c. Within that, we compiled, linked, and executed the application. And I just made one change on the main.c. Okay, the function, the user-defined function. The user-defined hello is the user-defined function that is invoked with some new argument. So the change is only on main.c. There is no change in the hello underscore fn.c. My question is, do we need this? Do we need to compile or recompile hello underscore fn.c? You got my question? We should not. Correct. So for that, what I am going to do, I am going to just compile. Yeah, this one, main.c. Just to compile this main.c again. What will happen? It will create a new main.o. Okay, new main.o will be there. Then I have to run the recent command main.o, the recently created main.o with update, and the old file hello underscore fn dot o, followed by hyphen o, new hello link 1. Now there is a new executable and we have created this one. So now let us run this. New hello link 1. So it should display the newly updated one called everyone. So based on this process, what we need to confirm is whenever there is a multiple files in your project, if you are making any changes on very minimal set of source codes, it is not necessary to recompile all the source codes, all the source files. It is mandatory to recompile those files which are updated. That is needed. So here we have recompiled main.c and created main.o, and we have not recompiled this LOFN because there was no change there at all. So, but linking for we need to obviously need to link with the newly created object, the executable, so that we are passing both of these arguments. Keep this in mind. It will be useful when we discuss something on Makefile. I told you, right? There is a tool called Makefile. It is a famous tool. You might have used that, but I am just giving you the introduction on those things. There, this side of avoiding certain recompilation is taken care by the main make tool automatically. It is not necessary to manually do that. The Makefile tool will take care of those execution on its own. That I will give you introduction later. I think up to now it is clear to everyone. I want to just confirm. Hope it is clear. Mm, For the sake of simplicity, I would like to give one more example, whether I have that or not. Let me check. Yeah, I have this example. Look at this example. It is having a main function included with math.h, stdio.h for printf, and we are invoking square root function so that math.h is used here. It is a function call. There is a function call. There is a function definition. There is a function declaration. Function call is in this file. Where is the function declaration? The function declaration should be part of this math.h like this. This is the function declaration, right? hello.h. Similarly, we have a math.h. Yeah, here, math.h. Where will be the function definition? The function definition will be part of the library, mathematics real library. It is a pre-compiled library. Got it? Static library. So I just initialized these two trying to display this. Let us check what will happen in Linux. GCC cal.c -o calculator. So it is giving me some undefined reference to square root, saying that the the linking process is doing something. During the linking process, there was some missing information in the program. Okay, so what it needs to be done? So this can be simply done by adding few more flags -lm, link the mathematics library. -l is similar to -o or something like that. -l is linking. The m letter is mentioned is for linking the mathematics library in Linux. If I do this, it will compile and it will create a linking process. Now I want to run that calculator. That's it. So I will be getting the response like this for the program. I just want to convey this -lm. Is it clear to everyone? Okay, we will move further with with certain examples. Um, I would like to create a file preprocessor.c. So within that, just include stdio.h main. So within that, I'm going to use some pre-processing directive if def test printf test mode. Just for debugging, I'm giving that end if printf that's it. So this is a very simple program where I have used two preprocessor directives, hash anything which starts or prefixed with the hash symbol is preprocessor directive. Even this hash include is a preprocessing directive because you know the first step in the tool chain of the compilation process is the preprocessor. What will happen? Any assumption? Before the real translation is going to happen in the compiler is having different stages. One is the pre-process stages, the translation which involves by itself the optimization. The optimized output will be the final outcome of the compiler. Any idea? Say for example, hash define grav followed by 9.6. What will happen? Any idea? Hash define grav. It is a word. Okay. This is the convention we have to use in most of the programming language. Whenever you define any pre-processing directives, those directives or constants used overall within the application can be must be defined or declared with upper cases. So these are all constants or directives, pre-processing directives. So what will happen in your program? This grav word will be replaced by 9.6 that you know very well. But when that will happen? That is what my question. Is that happen during the translation? Or is it happening before the translation? I mean the real compilation. This will happen in the pre-processing stage because hash define is a pre-processing directive. Grav is name of the constant. It is a symbolic constant. The constant is 9.6. It is very simple. We are giving a symbol to a constant. That's it. That is why it is called the symbolic constants. And wherever there is an instance of grav, that will be replaced by 9. Simple replacement will be done before the translation, before the real compilation. That replacement process will be carried out by the another system software called preprocessor. So the preprocessor is a software which is part of the compiler and that will be running during the first stage of the compilation. So before the compilation, the real object translation happens. This kind of replacement will be done by the preprocessor. That is why these directives are called preprocessor directives. It will simply replace this by 9.6. So this will become 9.6 before the translation, real translation. Does that make sense? Hello. Okay, let me proceed. If def, but within the function also, we are trying to access some directive like that. There is a grav, there is a test. Both are in uppercase. So this is also another directive, preprocessor directive. But In this code, what we are trying to do is we are checking whether is there is a test directive defined or not. If defined, test, do this. Got it? Then end of this if. Then finally running. This will be executed. If there is a pre-processing directive with the name test is defined, this printf will be executed. Otherwise, the execution will start from here. It's a kind of if-else process, but this if-else is not a compiled level C language code, but it is a pre-processor level code. Now I would like to compile this and run this. GCC. What is the name of the file? Preprocessor.c. So it is a warning. I am making that as float. Now it is compiled. So if you look at that, we have not used -o for redirection. That is why we will be end up with the a.out. If I run /a.out, I am getting running ... followed by 9.6. So it is showing this as the result. It is not at all executing this part. Why? Because there is no preprocessor directive called test is defined within the scope of the program. Unfortunately, there is no definition of test preprocessor directive directly on the code, but we can inject this directive from the execution environment or the compilation environment like that. Let me do that. This is injecting the directives from the execution. What I'm going to do now is I'm going to inject GCC -d, D for directive. I'm going to type the directive name test followed by preprocessor.c. Now it is done. Now if you run this a.out, we'll be getting the new printf also, this one. Earlier we have got only these two. Now we got test mode also. If you look at the code, it is running this. After that, it is displaying this two also. So within the program, we don't have the definition for test directive, but during the compilation itself, creating the object code itself, we are injecting the test directive by using -d for directive, -d followed by directive name test within this program, so that this program, while running this program, it accepts that there is a definition of test directive there, so that it is executing that code also. Is it clear to everyone? Great. Similarly, if you want to check what are the basic level system macros, the pre-processing directive is also known as macros. You can also view system macros by using cpp -d m for macro followed by dev/null. It will give you all the macros in the system level macros in the Ubuntu system. These are all set of macros used there with its values. If you look at that, uint least 16 type, that is referred as short unsigned int. This is long unsigned int. This is signed character. Instead of using this set of words, they will be using this one just for masking purpose. It is a kind of abstraction. That's it. This kind of abstraction mostly used in embedded application. I think everyone is clear with this concept. Is it clear? I want to extend this with some more fields, something like printf. I am passing one more variable directive num, but num is not defined. Let us do compilation. So it is saying that num undeclared. So what we have to do? We need to pass or inject via -d parameter -d num, which is equal to some 100 preprocessor.c. Now if I run a.out, I will get the result as 100. Value of num is 100. That is what we used in the program. And it skips this because we are not passing test. Now there is another way also. Suppose, for example, I can also pass something like this plus now look at that. Earlier we used a num equal to 100, that is directly displayed. Now we are passing that as a string 100 plus 200. This 100 plus 200 will be replaced here, and the replacement will be like this. So during the this num will be replaced by 100 plus 200. That is the pre-processing stage. Pre-processing stage is done. Then during the compilation and during the execution, this will be really executed as summation. Clear? So we like that we can play around with macros. Just I want to check, or the expanding the headers or the macros. Let us do that. GCC followed by -e for expanding the macros with preprocessor.c. So it has listed something. This is what the code, and it has involved too many number of declaration. You know, this file is having stdio.h. The header file, standard input output header file includes, I already told you, this header file includes all the predefined functions, all the predefined input output functions declaration. That is what we are visualizing here. Look at that. Get W, put W. Like that, it will display everything. It will list down everything. This also, yeah, look at this printf. It is going to accept constant character star. And comma dot dot means accept any number of arguments of this type, string type. You got my point? Is it clear to everyone? So far, do you have any questions? Great. I'll show you some code snippets, um, which will involve kind of optimization. Can you look at this? This is a simple arithmetic expression where cos of v multiplied by 1 plus sine of v by 2 plus sine of w multiplied by 1 minus sine of v by 2. Is there any common sub expression there? Do you find any common sub expression? You look at this. This is cos and sine different. This is sine u by 2, sine u by 2. I think this one is common. We cannot make this the entire sub expression as common because there is a addition here, there is a subtraction. So this one is the common sub expression. Will you accept this? So if you are trying to write a code like that, you know one thing, compiler is highly intelligent, and during the compilation itself, this will replace this common sub expression into a common variable. So what will happen? This entire expression will be split into two. So for example, first the sine of u by 2 will be assumed as some temp, this one. Then this entire expression, in this entire expression, this will be replaced by t. So this is what happened. So this is called common sub expression evaluation. So what is the purpose of this one? So it is not necessary to execute the same common sub expression again and again. Assume that if this is the single line without any loop or without any iteration, then it is not a problem. It does not consume any uh, it does not involve any time complexity. But assume if this line is part of any loop, which is having some millions of iteration, then at that point of time, why don't you modularize this? So this sub expression, common sub expression, can be assigned to t. So this will be executed only once, and this t can be temporary variable, can be used for wherever it is needed. Is it clear? This is one way of using optimization. You can, as a developer, you can do that, but unfortunately, the compiler will do the same thing for us. Do you have, you know the concept called inline functions? What is it? Inline function call. When will you use inline function calls instead of your normal function calls? Any idea? We use inline function to reduce function call overhead by inserting the function's code directly at the call set. Great. That is great. Say, for example, if you are using function calls like say, for example, you're having the function definition something like this. This function is just multiplying the same number argument with its own and return the value. So instead of that, why don't you directly use this multiplication directly wherever it is called? For example, in main function, if it is called sq of 44, this line can be replaced by, or if you pass some x, this can be replaced by x multiplied by x. That's it. This is inline way of calling it. It is not calling, but it is replacing the functionality by itself. So thereby, as someone said, thereby what we are enhancing over the program is, it is totally reducing the number of calls to this function. It is doing some very minimal calculation. Why don't you replace the entire function definition in the function call itself? That is what it is called inlining. This is also automatically taken care by the compiler whenever the compiler finds this set of minimal execution statements in a function call, so that it avoids the unnecessary function calls. Do you know what is the function call overhead? Whenever there is a function is called, what is the data structure behind the function calls? Any idea? What is the basic data structure behind the function call? Great, stack. Stack is the very important data structure, and it is behind, it is playing vital role in the entire compilation, linking, as well as loading. Wherever there is a tool chain cycle, stack plays a vital role. Can you tell me one simple example of stack during compilation, not running, during runtime? Not during runtime, I am asking about compile time. Compile time example of stack. Give your own thoughts. I request not to search in any external sites. Just want the answer from your own. The compile time example of stack. Any idea? Let me do one thing. Here in this program, I'm just going to add one more curly brace. It's a preprocessor.c, right? I am coming back and GCC preprocessor.c. So what it is showing? Expected identifier is before this token. So in our program, we mistakenly added one more closing curly braces. This is identified by the compiler itself. Before compilation or during the compilation itself, something is done by stack. This is the implementation of, this is the response we are getting, right? Some identifier is needed. So whenever there is a close, there should be an open curly braces equivalent to that. Which data structure is maintaining that during the compilation? Stack is the data structure which is used, which is maintaining or which is balancing the parenthesis. You might have heard this, balancing the parenthesis of each and every tokens in this program. Each and everything is a token in this program for the compiler. So whenever there is a open, there should be a close. Whenever there is a close, there must be a open equivalent to that. That is why it is checking. Can you tell me how it is happening? How the stack is identifying that this is a error? Very simple. Whenever there is a open parenthesis, that will be pushed into the stack. Let me do that. Stack. Initially it is empty. So I'm just focusing on the curly braces. So where there is an open curly brace, it is pushed into the stack. And it iterates each and everything. And there is an occurrence of close curly brace. So whenever there is a close curly brace, it looks into the stack. And if there is an equivalent open curly brace, that will be popped. So this is popped. So now the stack is empty. Unfortunately, it identifies one more curly brace, but it checks for the stack equivalents open curly brace, but unfortunately the stack is empty. So at this moment, throws such kind of errors. That is the example of stack or the implementation of stack during the compilation. Does that make sense? Everyone is clear with this? Guys, great. Okay, I think we are reaching the end of the session, 7:30. Still, we have 10 more minutes. I would like to cover up certain things quickly. I have a file. Let me check optimize one. Yeah, there is an optimize one.c program which is having some simple code, a main function within the main function. So there is a single for loop, but the number of invariants is very high. Number of loop iteration is very high. Just for the sake of explanation purpose, I just increased the number of iteration as the highest one. And there I am going to call power n function with two arguments. Power n function is defined here, which is accepting two arguments, which is doing some calculation over here. Power of n, that's it. D times d power n. So this operation is carried out by this for loop. So definitely this function, this file execution will take more time, right? Let us run this program step by step with a different kind of optimization levels. Okay. Come back to this. First, let us compile this code. In GCC, we do have a different level of optimizations with the parameter called capital O. Hyphen small o is for creating the final executable. Hyphen C for creating only the compiled output. Hyphen capital E for exploring the macros. Hyphen capital O for optimization. So we do have different level of optimization. Zeroth level is the default optimization. Level 1 is the optimization with function unrolling. Hyphen 2 with loop unrolling. Hyphen 3 is combination of these two. Like that, we have basic 4 levels of optimization in it in the GCC. Let us do one by one and run the application how it is looking like that. GCC hyphen capital O 0, zeroth optimization. The name of the file is optimize.c. I did that. I didn't mention any output file, so I have to run .a.out. It is giving the response of the program. But based on this, we cannot explore anything. So that what I'm going to do is, I'm going to add time. I'm going to run the command time and pass a.out. So when you pass any function or any executable file as an argument to time, it will mention how much time it has taken for execution of the particular application. Fortunately, it has written 3 parameters: real execution time, user execution time, system execution time. User execution time is the real user execution time is the real execution time, the time taken for the particular application to run. That's it. The real one is the time which has taken for, say for example, when you run the program or when you run an application, it might take some time to wait for some other resources to be cleared. Those entire cycle, the time cycle will be considered by real time. The user time does not look at it. User time is only focusing on the application time, excluding the waiting time, turnaround time, something like that, latencies. System time involves the time taken for the operating system to process it. So at this moment, 1.00066 is the real time. 1.065 second is taken by the user execution time, the real execution time. There is no operating system time taken for this explicitly. For this -o 0 compilation. Now I am going to compile the same program with another level. GCC -O level 1 optimize.c. Now I am going to run the application with dot. Now look at that. It was 1 point something. Now it is 0.255 on applying the optimization 1 level. So drastically there is a change, right? 1/4 time it has reduced. Now let us move on to another level of optimization. Optimization 2. time dot slash a dot out. So optimization 3, level 2, significantly the time has improved, increased. But when comparing to optimization level 1, as of now, optimization level 1 is giving the better result for this program, especially. Let us move on to the other one, hyphen capital O 3. So this optimization 3 and optimization 1 are almost nearing to each other. But comparatively, optimization level 1 is giving the better performance as of now. There is an explicit functional parameter can also be passed. I can also explore that. Hyphen O, third level. Within the third level, there is a parameter unroll, unrolling of loops that you might have studied in your basic level compilation process. It has significantly reduced the time, even when comparing with the O1. So the O3 gives 267, 0.267, but along with the unrolling of loops, it has reduced significantly. So thereby we can compare the performance of the optimization strategies. Is this clear to everyone? Fine. Before concluding the session, I told you there is an usage of the make file, right? I have a simple example for make file here. Look at this. Make file. The structure of the make file is the execution of the make file goes from bottom to top. First of all, the first, this one, this is representing the target. So target means I'm dynamically creating the C program in this sequence. Echo hash include yesterday io.h into main something hello, something like that. And that is redirected to test.c. So this test.c file is created and that is going to be the target. The target, I'm going to, the execution as I already told, execution starts bottom to top. Once test.c, what will happen? It has to create a target file, test.o. For creating the test.o target file, this is the input, test.c. What will happen? This is an execution. gcc hyphen c test.c hyphen o test.o. This will be executed first. Once test.o is generated, what will happen? It will be the input to the target test. Test.o hyphen o test will be generated. So finally, what is the output? Test.o. Initially, test.c, test.o is the second output, test is the final output. Let me run this. How to run? It is very simple. Make. Just type make. It will execute this. Then finally, you can run the program. That's it. Sorry, it is the previous one. Here it is. We need to run the dot slash test. Yeah, hello is the outcome. This is the simple way of compiling and running the multiple application, multiple source files in a C program using the make utility. Make is the command to run. The name of the file should be like this, M capital single word make file. I hope this session is useful to you. If you have any queries, please ask. Am I audible?
Yes, sir.
If you have any questions, please let me know.
So before winding up the session, on behalf of the student body, I would like to thank you so much for joining us today and walking us through these concepts in compiler design.
Thank you.
Your session has given us a lot to think about and learn from, and I'm sure everybody over here will relate with me on this. Really appreciate that you took the time out of your busy schedule to be with us here and guide us. Thank you so much once again, and we really look forward to learning from you again in the future. Thank you so much, sir.
Thank you so much. Thank you. Thank you all. Thanks for the opportunity.